spend a couple of minutes talk about something related to your practical sessions. The reason for that is because I got some feedback from some of our tutors. So the first one was some of you, say for example, some of you are still don't know, seems like, okay, to our tutor, don't know the meaning of import. That is the first feedback I got from our tutors. And another one is that some of you get really scared, seems like, okay, frustrated when you see error message. Don't be. I think error message, seeing error message is quite common in practicals. And it is a good thing. It helps you to find out what's the problem. Now, just address these two issues. Okay, first about import. Let's have a quick look without this line. Okay, if I run my code, because I have already, let me start a new one. New Python code. Okay, so here everything is new. Let me say I want to generate an array in my new file here. I paste it and I run it. This is an error message we have got here. So what does it tell us? It says NP is not defined. So why NP is not defined? Because it seems like I call for a function array from NP. So NP is not defined. Now you can see what is NP. So I import from here. NP is the shorter name for this one, for NumPy. Okay, so NumPy is a package, includes many classes in it and functions. So here, rather than call it NumPy, or I can use, say, just use UPY here. Let's see. Okay, we can get it. There's no error message anymore. And I don't want to every time type a long name NumPy. Rather, I want to have a short name. I just call it N, for example. It can work. It is the name. It's just a name you give it, and then I can call it NP. Yeah. So this is name. So import. What does it mean by import? To use some functions, you need import the corresponding packages or packages. Okay, so here this array function is from this package. Another example is that, for example, remember we talk about PCA. We use this toy data set. This is our toy data set, and I want to plot it. This is the function we use. So run it. This time I got error message again. Plot is not defined. So I think by now you should know in Python, if you want to plot something, you need import is matplotlib, right? So that is why we import here. Again, this PLT is just a name. I don't want to use the whole thing here. It's too long. So rather than use PLT or PLOT, I call it PLOT, because here I call it PLOT plot. So we run it this time. We get the figure. So don't be scared by seeing error messages, okay? It is a help for you to understand what's going on, what's wrong. Now, another way to learn is that many students said, I don't know how to use this. What does it mean, this S? So what about here? You change it. So, you see the shape. this is the shape, or you can change it to here, right? How do I know what markers can I use? Then you Google it from, for example, online to see what is this function, and then what are the arguments you can use. Here, X, Y are the data points, and the I's is an array. What does it mean? And the C, array like list of colors. C can be used to define colors. So let's say, for example, I want to use this color. Then what do? It is array. And what can I do about it? I can add a little bit more to here. It is array. So run it again. This time. That is because I don't have this here. Let me see. Paste. Yeah, this time. Sorry, just now. Right. What do we have? We have different color. So how you can define color by giving different code here. How did I know this? I just checked, the function, the web page about, document about this, how to use this function. Then I get all information by looking at this document. Yeah, you can define the different markers and the colors using this way. So the 2 points from our tutors, the feedback, okay? One is when you see the error messages, don't be afraid, okay? It's okay. It is a learning, okay? You learn from this error message. Another one is import. What does it mean, import? Import, to use this function for plotting, say scatter and plot, you need to import the corresponding packages. So this one is for plotting, and this one can be used for, generate array. Okay, that is a little bit about practical feedback from our tutors. Now, we are behind this, but let's start about today's lecture. So, here, okay, today is very important. The 5 steps of data science. Sorry. Learning outcomes. At the end of this session, you should know what are those 5 steps of data science. And the aim of splitting data, the data matrix, to a training set, a validation set, and a test set. Okay? By the end of this session, these are 2 things you must know.
I guess you forgot to record the session?
Right. Okay. Thank you. Okay. Okay. In my notes, I will record it now from this page. Okay. So let's start. Thank you, Mano.
Recording in progress.
So 5 steps. Number 1, step 1, asking an interesting question. Number 2, obtaining the data. 3, exploring the data, modeling the data, communicating and visualizing the results. One thing I need to emphasize here is that in practice, that is when you do in real life application, you may find yourself, okay, working in a loop of 5 steps. It's not something like you start from here and then your ending at here is done. It's quite often what happens is, for example, after modeling the data, you may find the model can be further improved by adding more features or remove some features. So you have to go back to here, adding more features, you need to obtain some new data. And then you need to explore your data again, remodeling the data. So it is a loop. Now, let's have a look at each step in details. First, asking an interesting question. You may be given the question, That is, your customer may ask the questions directly to you, or your boss may assign some specific tasks for you to solve. Okay? Or you may have a proposal, but there's no specific research questions yet. That is, for example, quite often our PhD students, when they start their research, they may know a research topic they may would like to work on, but research questions are not clearly defined. Then what you need to do? You need to do lots of comprehensive literature review to identify the research gap. And then based on the research gaps, you can ask a research question. So at this stage, you need to work closely with people in the problem domain. So have a look at here, this paragraph by yourself. Okay, once the question is defined, you need to think about what methods can be used to solve the problem. For example, do I need to use, this is a supervised learning problem or unsupervised learning problem? Okay, so this is the first stage of asking an interesting question. Once you have selected the question you want to focus on, you need to think about what data you need to have and what data are available to answer your research questions. Here are two examples from our PhD student PhD projects. So the first one is about correcting errors in optical data transmission using machine learning methods. The data set includes many signal waves. Each signal belongs to one of here 4 classes, and each signal consists of 64 complex values. So you can imagine in front of you, there's a data matrix, and it may have 1,000 rows, 64 columns. Each value in this data matrix is a complex value. So that is for this PhD project, what the data looked like. Another project is about image processing, this one. So the data set includes some images collected from deep astronomical imaging surveys. The aim was to investigate whether those objects, for example here and here, in these images can be clustered using unsupervised learning. So you see, this one data set is a data matrix, complex values. Here is data matrix includes many images. Here are 2 projects from our past MSc projects. So the first one again is a image processing project. Okay, so that is using machine learning techniques to recover particles, actually ice particles size from 2-dimensional light scattering patterns. So properties of cloud particles affect climate and weather. Better understanding of cloud particles are essential for the understanding of present climate and climate change. So here we wish to derive single particle properties, for example, the size, from their 2D scattering pattern images. So from each these images, okay, each image here, we can derive single property for each particle. The last example here, this is a structured data set. Okay, the aim is to giving lots of different chemical compounds with 5 different features here to estimate either their ER values as a regression problem or classify them into 0 and 1, 2 classes. So far, data in all these 4 examples or provided by researchers in the problem domain. Sometimes you find you have to collect data by yourself. Some data can be obtained from internet for free, but if you need to collect some data involving human participants, then you need to apply for ethical approval first. Data can be, here is another example. Data can be text data. They appear in natural language processing applications. As you have already seen, data can be text data, images data, real-valued data, complex value data. Data can also be sequence data, or we say time series data. So when you obtain data, you need to bear this in mind. What type of data are you going to work on? Now, very important stage, the third stage, exploring the data. After the data is collected, you should spend some time in learning about the knowledge in the problem domain. It will help you to understand which features may be used in the next stage, for analyzing the data. And the aim is for you to understand, the features of the predictors. Or predictors, do you remember in our simple linear regression lecture? Predictors are also called independent variables. And the aim for this stage is also for you to understand the relationships among the predictors. And we want to be able to understand our data a bit more than when we first found them. So what methods can be used at this stage? We can use unsupervised learning algorithm, for example, principal component analysis, to help us to find structures, natural structures in the data set, whether there's a cluster of information, whether there are some outliers in the data set. And we can use some scatter plots, right? The aim for using scatter plots is to see whether there's any correlation between two features. When doing data exploration, there are some basic questions you need to ask, you must to check. Okay, so for example here, I list some of them. Is the data organized or not? In our pre-recorded videos in Unit 1, we talk about structured data, unstructured data. Okay, if data is unstructured, you need to transfer them into row and column structure. You need to know what does each row represent, what does each column represent, okay? Are there any missing data points? What does it mean, missing data points? So for example here, in this structured data, if we have, say for example, 200 chemical compounds, each row here represents each one single chemical compound. And let's see, for example, for the second row here, this hydrogen bond value here is missing. It's missing. Then we call this row has a missing value. So what do you do when we have missing value in the data set? It really depends on the situation. Say, for example, if you have many data points, you really don't mind whether there's a one or two missing values in one or two rows. If that is the case, you can simply remove those remove those rows involving missing values. However, if say you have only 20 compounds and 2 or 3 of them have these missing values, then you cannot afford to remove them simply. You need have a way to fill in those missing values. For example, one way to do that, some people just use the mean of that corresponding feature to fill missing values. But that is something you need to bear in mind to think about it, okay? And so this is about missing data. Now, do we need to perform any transformations on the columns? So what does it mean here? So for example, data normalization we are talking about. Why do we need data normalization? So have a look at here. I prepared an example here. Let's say, again, two compounds, chemical compounds. Okay, we have two features, molecular weights and the hydrogen bond numbers here. The first compound, we have values for 309. The second one, we have 101. If we don't normalize them, use the original value, if we calculate the distance between the two compounds using Euclidean distance. Okay, Euclidean distance is defined here. The first attributes, that is molecular weight, from the first compound minus the first element, first attribute from the second compound. And then here is the difference between the second attributes from two compounds. So as you can see, because my first features here, the magnitude is much larger than my second feature here. When we calculate Euclidean distance, the distance, final distance, the value of final distance is dominated by the first feature. Although, if we consider hydrogen bond here only, the difference here between these two compounds actually is quite large. But it seems like the feature didn't contribute very much to the final distance, right? So why do we need to calculate this Euclid distance? Can you give me an example? I know, you have already learned K-means algorithm as an unsupervised learning in machine learning and a neural network module, right? For K-means, we need to calculate Euclidean distance maybe. So when you use a metric like Euclidean distance, it's better to normalize your data first before you calculate this distance, so that every single feature here can contribute to this distance. Not, this distance is only dominated by only one feature. So that's why one way to normalize our data, transfer data, original data, is minus mean and then divided by standard deviation. So here, two compounds, the mean value for each feature, 205 respectively, and then standard deviation is here. So after apply this transformation equation, those are new normalized data. And then we can calculate the distance. This time, as you can see, both attributes contribute equally to the final distance. So that's why considering, see here, do we need to perform any transformation on the columns? We need to think about it, okay? Another example we have already seen is that normalize each column into a range between 0 to 1 when we talk about gradient descent algorithm in that linear regression example. Okay. Some other questions. Is the data set balanced or imbalanced? What does it mean here? That is something you must consider when you are dealing with a classification problem. So for example, we have two classes in a classification problem. In class A, we have 100 data points. And in class B, we have 3. So the ratio between A to B is highly greater than 1. This data set is called imbalanced. When we have an imbalanced data set, if you do classification quite often, the results actually is dominated by, we call this majority class. So when we have an imbalanced data set, normally what do you do? First, you need to balance your data set. Okay, so that the ratio between majority class to the minority class can be reached to roughly about 1. So have a look at this example here. Again, we have two classes, class 1, class 2. Class 1, we have 50 data points. Class 2, we have 45. So this data set can be, although the ratio is not exact 1, but we can treat it as a balanced data set. Okay. Finally, is there any inconsistent data points? What does it mean here? Inconsistent data points can appear in both regression problem and classification problem. For example, here, we have some students' records. We want to use one feature, predictor or independent variable, that is students' study time, to predict students' English score. For student 1 and 2, both spent 5 hours study. However, their scores are different. One is 80, one is 70. These two rows are called inconsistent data points. Okay, because they have the same independent variables but different dependent variables. Okay, so based on these two data points, we may have different estimation, which one we should use, right? So when you have a data set like this, if you have already identified some inconsistent data points in the data set, either you can remove one of them, depends on the applications, or you need to consider add one more different attribute, or so that we can cope with this inconsistent problem. Okay, either remove one of them, we need to think which one should be removed, if that is possible, or try to think add more different independent variables to solve this inconsistent problem. So we are in this data exploration stage. Some basic questions that is you must ask whenever you work on the data set. You are giving. It doesn't matter which data set you are giving. You need to think about these basic questions. So this is the stage 3. Now, stage 4, modeling the data. Modeling the data includes model tuning and model performance. These two here. Okay. This step involves the use of statistical methods and machine learning models. In this step, we are not only fitting and choosing models, we are implanting mathematical performance metrics in order to quantify the models and their effectiveness. For supervised learning and unsupervised learning, we have different performance metrics to use. Okay? So, for example, for regression problem, supervised learning, okay, we have mean squared error, which we have already seen when we learn simple linear regression. But if we consider supervised classification problem, when the data set is balanced, we just talk about balanced data set, that is 2 classes or 3 classes, the ratio among them or between 2 classes are about 1. Then we can use accuracy rate. Otherwise, a safe way is always to use confusion matrix for classification problem. Okay, confusion matrix can be used for both imbalanced data set and balanced data set. So this is the confusion matrix. We basically can divide it based on the labels, actual labels, into 2 classes, positive, negative, and then we can divide our predictions into positive, and negative. So we have 4 entries here. true negatives, true positives, false positives, and false negatives. When we talk about the accuracy rate here, that is, in the numerator here, we have true positive plus true negatives. For the sum of here, the denominator, it is the sum of all 4 entries is here. Okay, for other, based on this confusion matrix, we can also define other performance metrics, which we are not going to talk about too much details here. However, you should know all these 3 are used for supervised learning. What about for unsupervised learning? Since you have already learned k-means, do you remember? Quantization error can be used to measure how good the clustering is, right? So these are some methods you can use to measure the performance. Many modern classification and regression models are capable of modeling complex relationships. However, they are very easily overemphasized patterns that are not reproducible. What does it mean? Have a look at here. I have 2 classes. One is, represented by the circle points, and the other ones we use cross signs to denote the other class. So this data point, okay, quite likely, quite often, this can be a error, okay, measured by introduce some error. It could be. So when we produce a classifier decision boundary between 2 classes, if we put decision boundary here, then quite often when we make predictions for a new unseen data point, which should belong to this class, for this point here, then it can be misclassified by this class. Rather, for this case, we would consider our decision boundary in this position. Okay, that means we would like to ignore this misclassification in the training side. So what I said just now is many modern classification and regression models are capable of modeling complex relationships. However, they are very easily overemphasize patterns that are not reproducible. Therefore, we need to have a methodological approach to evaluating models. So what is this approach? That is the method we are going to talk about. Almost all machine learning algorithms have tuning parameters that enable the model to flex to find the structure in the data. For example, consider to use simple linear regression method. Do you remember last time when we talked about we can use, if the data set has some nonlinear nature in the data set, when we use simple linear regression, we may use polynomial features to capture that nonlinear nature. Remember that? So we must use existing data to identify settings for the model's parameters, right? That produce the best and the most realistic predictive performance, right? Shall we use polynomial feature or not? Shall we use, if we use polynomial feature, shall we use interaction between 2 terms, or shall we use, a feature to the power of 2 only? Right? Traditionally, this can be done by splitting the existing data into training, validation, and the test sets. So let's have a look at here, training set. Training set is used to determine values of parameters. So for example, when we consider a linear regression model, A0 plus A1 multiplied by the first feature. So A0 and A1 are coefficients Those are the parameters for the model. Okay, so training set is used to estimate those values. Validation set used to tune the model's hyperparameters and to evaluate accuracy of the model. What is this hyperparameters? They are user preset parameters. For example, I mentioned, okay, shall we use, for the same data set, shall we use polynomial features, or shall we use simple linear, just a0 plus a1x, or shall we use a0 plus a1 x1 plus a2 x1 to the power of 2? So this difference, the difference between two models actually is a hyperparameter. You can set, you as the user, into preset which you would like to use. Test set. The selected model should be further tested by measuring its accuracy on a third independent set of data. That is, okay, this is really, really important. That is, the model should be evaluated on samples that were not used to build or fine-tune the model. What does it mean? So there shouldn't be an overlap between your test set and to here, training set and validation set. All data points in the test set are unseen data. Okay, they are not part of training set, not part of here validation set. So let's have a look at here. Let's see whether I can explain this clearly using this figure. Okay, please bear with me about my handwritten. Okay, it's not easy to write well using here. But anyway, imagine we have a data matrix. The first several columns are the inputs or features we want to use to train a model. The last column here are the targets. Can be class labels, can be some real values for regression model. So I divide this data set into three parts. Here, brown part, here, that is the training set. Usually it's about 2/3 of the whole data set. And here, this part, this same part, this one, we call it validation set. The last part, we call it test set. It would be good as a habit, okay, it's a good habit. When you are giving a data set, try to shuffle your data set first so that when we do a classification problem here, every class can be uniformly distributed in all these three parts. Okay, now we divide our data into three parts: training set, validation set, and test set. Now what? You want to train a model. The training set has two parts. One is inputs and targets. Both parts will be sent to a model. We train the model using the training set to decide, okay, the parameters. So for example here, let's think about the first model has this shape: A0, A1, A2, and then A3. We have three features. One is feature 1, feature 2. The third one is the interaction between these two. So the aim using training set is to decide values for A01, A1, A2, and A3. After we train the model, the trained model should be validated on the validation set. Okay, so validation set is used to measure the model's performance and also used to decide which user preset parameter value we should use, hyperparameter value. So here we have two. One is, I don't know which model I should use, so I use two. This one, this is my first one, and then I also have the second one. Rather use interaction between two features, I use power of 2 for each of these features. So which two models, which one of these is good better to use for the given data set. That is something I don't know. So as user, I preset these two models for here, to learn. So let's say we try the first model. We got the parameters for A0, A1, A2, A3. And then we validate model on the validation side. Then what? Validation side input goes to train the model. We will get predictions. Predictions will be compared with the target from the same validation side. Okay, how do we compare them? We can use mean squared error if that is a linear regression problem. We can use accuracy rate or confusion matrix if it is a classification problem. Okay, after we do the whole thing here, now we move on. To train the second model using the same training set. And then we try to use the same training set but different model, and then we can get A0, A1, A2, A3, A4. Once the model is fixed here, again, we use the same validation set with the same input to this model, the trained model. You get new predictions. This time, compare the new predictions with the target value from the validation set and get a new performance. Now you are ready to say, okay, using the validation set to see which model can give a better performance on the data set. So let's say, for example, the second one gives better results compared with the first model. Then you say, okay, I want to use for this data set maybe the second model. Now you need to decide whether this model is good enough on an independent test side. That is, this part. Okay, and then report the final performance measurements. So this is the whole procedure for model selection. What I want to emphasize here is that always use parameters extracted from the training set to normalize the validation set and the test set. Remember what I mentioned, so this parameter is not A1, A2, A0 for linear regression. This is something from a training set. So remember here, we talk about Euclidean distance, right? So what I mean value here, you see, should and standard deviation, they are parameters. They should be extracted from training set only, not the whole set, not the test set, not the validation set, but the whole training set. And then you use that mean and the standard deviation to normalize training set, validation set, and the test set. That is what we meant here. Okay, so I think we have already mentioned this one. Okay, so here, training set, validation set, this one. I mentioned this is for a simple random sample. That is what I meant earlier. See, it's better when you are giving a data set, before you split your data into training set, test set, validation set, you better shuffle your data first. Okay, for an imbalanced data set, remember we talk about imbalanced data set. When splitting the data, it is important to keep the ratio of the minority to majority in all those three sides. Okay, so if what you don't want to happen is all minority data points are assigned into training set. There's no minority points for these two. Validation set and test set. That is not something you want to do, okay? So you want to keep majority to minority, the ratio is equal to both to training set, validation set, and the test set. So sometimes when we have very small data set, okay, we cannot afford to divide our data set into a training set, validation, and test set. Then what do? We use a technique called leave one out. So for example here. So let's see. This is a very extreme case. I don't think you should use that. But anyway, let's just consider we have only 5 data points in the data set. So what is this leave one out? Leave one out means, okay, each time there's one point is used for testing. All the others goes to training set. Okay, so if you want to use validation set here, then you have training set will be 1, 2, 3. Validation set is 4, test is 5. Okay, but quite often for this one, see, we just consider training and test. So for training, let's say we have 1, 2, 3, 4. So for the next one, this is a iterative procedure. Next one, the test point will be number 4. And data point 1, 2, 3, 5 are used to set up the training set. In the third step, we use the third data point here as the test point. All the other data points goes to training set. So in this way, every data point will be tested once. So eventually, after you run all these 5 times, the performance should be measured is a mean performance measurement over all these 5 test points. So it is called leave one out. That means for the test point, each time you use one of these data points. This works for very small data set when we cannot afford, to divide our data set into 3 parts. So here, that is a very important topic here. What is this? This is learning curve. Learning curve is a picture of the behavior of training set and the validation set performance against a parameter in the training procedure. For example, here, let's consider we are using the gradient descent algorithm to find the parameters of a simple linear regression. So here is the iteration step against the error. Okay, since the goal is to find the best generalization performance. What is the generalization performance? That is, we talk about here. I want to say we talk about here. This is our training set, okay? And this case won't give a good generalization because when we have a test point, for example, test point belongs to this class, but if that is in this, this area, then it would be misclassified. So good generalization means when you train a model, the model can have a good performance on your test set, not only on your training set, but also important, very important, it should have the good generalization on your test set. So the goal, is to find the best generalization performance. It suggests that the training should be stopped at this point. Why is that? Because it corresponds to the minimum of the training, both training and validation error. Okay. Also here, training at this step, the error seems even smaller than here. However, the validation set has increased. So this is not the steps we should stop here. That is the iteration number we should use. So we are looking for a minimum point, not only for the training side, but also for the validation side. So this is learning curve. So learning curve, that is a picture of the behavior of training side and the validation side performance against a parameter in the training procedure. When the model overfits a small data set, what does it mean overfit? So that means overfitting, it means the model has a very good performance on the training side, but not on the validation or test side. And underfit, what does it mean? It means underfit, it means the model has very poor performance on both training and the validation side. For example, here, overfitting. Okay, we have a training error curve here. We have a validation error curve here. Training error you can see has a very low error here. That is good. However, the validation error are very high. The gap between these two curves are large. This is called overfitting. That is something we don't want it, okay? We want to avoid overfitting. On the other hand, we also, of course, we want to avoid underfitting, okay? Both overfitting and underfitting are not good. So underfitting here, see, both errors for training, I think this is the training. Okay, I didn't mention here. This one is the training. And then here is the validation. Okay, I don't know if I can. So what I mean is this one is validation. Set curve. Okay, this one is training side. So as you can see, even for the training side, the error is very high. Okay, and when the training side size increases, we want to add more data points with a large data set, the error actually increases. And even for the beginning, the error is very high. The validation side, although it decreases, it seems like decreases, but it's still very high. This means if you have a learning curve like this, this means this is a model is underfitting. That is what we want to say here. Okay? So quite often, if a model trained properly, a model will never, except for by chance, give a lower error to the validation side than the training side. Okay, so the training side usually has a lower error than the validation side. Now, have a look at here. How to choose between models. 3 steps. First step, start with several models. Okay, what are those you start with? Those models have a high likelihood of producing the empirically good results, most accurate. Okay, start with those models. Then investigate simpler models. Then consider using the simplest model that reasonably approximates the performance of the more complex models. Because here we tried more complex model. Eventually, we want to use as simple as possible for a model, but that can reach, a good performance, just like the complex model can do. Using this methodology, this is the methodology we propose here. Using this methodology, we can discover the performance ceiling for the data set before setting on a model. In many cases, a range of models will be equivalent in terms of performance. So we can weight the benefits of different methodologies. When we see the benefits, we can consider computational complexity, ease of prediction, and interpretability. For example, a nonlinear support vector machine, I think you will learn in neural network and machine learning. Okay, basically it's a nonlinear method. May have a very good low mean square error, but it cannot export a prediction equation. Okay, so which makes it like a black box. However, if a more interpretable model, for example, a simple linear regression model, it can give the similar accuracy or similar mean squared error, then we may consider to use linear regression because the implementation of the prediction equation would be easy and would also have shorter running time. Okay, so this is the methodology we have been proposed here, starting with some models which can have high likelihood produce very accurate performance, and then investigate some simpler model. Finally, choose the simplest model that can give you reasonably good results, like those good models, those complex models. So, if our predictions or models is underperforming, what can we do? There are many things you can do. Okay, depends on whether that is overfitting or underfitting. If underfitting, you may consider add more features into the data set, obtaining the data that is part of. But for you, at the moment, all you need to know is, again, don't panic when you see, it's underperforming. There are so many things you can do. But the ability to determine what steps will improve your model, here, this ability needs lots of practice and also needs you to think critically, okay? That is one thing I would like to emphasize. When we ask students, say, write some discussion in critical thinking, rather than give us critical thinking, that means, see, for example, you generate a PCA plot. What can you see from that plot? Okay, what do you want your reader to see from that plot? Can you see any clustering information there? Can you see any outliers? And why one data point is far away from the majority data points? Those are the discussion in critical thinking. But what we saw from previous submissions, many students, rather than discussing critical thinking, they provide lots of procedures. How did they generate the figure? Those are two different things. So this ability can be trained, can be improved, but needs lots of practice. Okay. Finally, here, I'm not reading it out for you. I give you 1 minute. Have a look at here by yourself. So, representing your results in your report is very important step. Okay, it's not just like you put your figures into the report and then say nothing about it. That is done. That is wrong. Okay, you need to put results there and then give your analysis. You see, I said earlier, see discussions about those figures and tells your audience, your readers, what you want them to see from those results. That is very important. So 5 steps. Do you remember which 5? Asking, number 1, asking interesting question, obtaining the data, exploring the data, modeling the data, finally visualizing, communicating the results. I'm about 10 minutes late for this. That is because on the beginning I used about 10 minutes talk about Python. So before we finish, let's have a look at a case study altogether. And then I want to say one more thing about feature selection. Now, case study. Case study comes from one of our MSc students' project. So here, that is the data set she obtained from researchers in the pharmaceutical field. The first column here is just the compound. You know, the researcher shows, this compound, number 29, comes from a journal. You know, they use a different number to denote a different journal. And then use this 605 to denote which volume of this journal the compound is found in that volume, in that journal. Okay, so this first column shouldn't be used for the final analyzing the data. And then we have 1, 2, 3, 4, 5 columns. These are the compounds, attributes, features for each compound. Hydrogen bond, C chain, carbon chain, and molecular weights, log P value, log S value, solubility value here. The aim is either predict each compound's ER value, okay, ER value, that is enhancer ratio, okay, either predict this ratio or classify each compound into class good enhancer or bad poor enhancer. Okay, so given a data set, we have 2 possibilities. One is regression problem, one is classification problem. Now, in the problem domain, researchers use this equation, this tool, to predict this ER value. So the question comes from researchers is that, for us, is to, do you have any models or modeling methods which can provide us much better, much accurate estimations compared with these 2 methods we use? Okay, so interesting question. This one is asked by the researchers in the problem domain. The data obtained directly from the problem domain. Next step, we need to do data exploration. So here are only two plots generated by our MSc student. She actually plotted box plots for all those features, and each box here is corresponding to poor ER chemical compounds. Here is corresponding to good ER enhancers. And she also used, this is PCA plot, to visualize the whole data set. And the conclusion is that the 2 classes cannot be distinguished linearly. Okay, so can be a difficult question. And as you can see, this is imbalanced data set because majority data points belongs to poor ER chemical compounds. Okay, only minority belongs to ER greater than or equal to 10. So the student in the data exploration stage also did sampling. Okay, so that she used both undersampling and oversampling. Undersampling means remove some samples from the majority class. Oversampling, she used SMOTE, okay, SMOTE method to oversample some minority class. So that we are not going to cover here. I just try to help you to understand how a MSc student used those 5 steps in her analysis. Now, when she's doing this modeling for her project, she considered both classification and regression. So method used for classification, she used support vector machine, k-nearest neighbor. For regression, she used k-nearest neighbor and also Gaussian process regression. Performance measurements, she used the confusion matrix for classification, and she used the mean squared error and correlation coefficients for regression. Okay, and during the modeling, she divided her data set into training, validation, and test set. One thing is important for her project is that because the data set is in balance, she did sampling. However, this sampling shouldn't be done to the test set. Okay, so what she did was she divided the data set into training, validation set, and the test set. And then she did sampling in the training set only. Finally, she showed the results. Okay, confusion, this is just one of the examples. She has so many results. This is just one confusion matrix. She repeat her experiments many times. So she didn't just generate one test set. What she did is she repeat the procedure 10 times, for example, 10 times, and each time she randomly select a test set. That is why here is a mean value and with standard deviation. In this way, she thinks the results can be more robust. And she also found those wrong, misclassified patterns. She tried to visualize them in the PCA plot. Why these, you see, false negative, and false positive, why those chemicals were misclassified. So she provided the index for those chemicals to the researchers in the problem domain and talk to them, ask them to, to see why. Is there any structure from molecular structure, for example, for here, are very similar to this data point or not? Why this one is misclassified? You see, try to find that is communicating and visualize results. So this is one of project we mentioned. The last slide for this lecture is about this. So far in this module, you have learned one method that is feature extraction can be done using principal component analysis. Now, today we talk about a bit different method, a feature selection method. Okay, so this is not a theoretical method. It's just a procedure. I give you 1 minute, have a look at the procedure by yourself, and then we have a look at an example together. Okay, so what does it mean here? What's going on? Let's have a look at here. Imagine we have a data set involving 6 attributes, 6 features. Sorry, I think I made a mistake here. Okay, so 6 features here. First step, calculate correlation for these 6 features for the data set. Along the main diagonal line, what values shall we have? They should be all equal to 1. Okay, we talk about correlation coefficients. So correlation coefficients are values between -1 to 1. Now, The first step, calculate this. Second step, determine two predictors associated with the largest absolute pairwise correlation. For example, here, L1, I call it. So L1 has the largest absolute correlation between the first feature and the third feature. Okay, so back to that slide, that is my feature A and the feature B. Then the third step, okay, just one more thing. Why I said, absolute value here? Because we consider the correlation can be negative correlated, can be positive correlated. So the sign is not important here, but the absolute value here is important. So now we know A and B, that is my F1 and F3 are highly correlated. I want to remove one of them from my features. So which one I should remove? Now, based on the third step, determine the average correlation between A and all other variables. So A is my F1, and what about average correlation from F1 to F2 to F4 to F5 and F6? Find out those values, calculate the average. Similarly to B, B is my F3 here. So find out the average value from F3 to F2, F4, F5, and F6. And then compare the average of these two values. Okay? If the average 1 is greater than average 2, it tells us this A is highly correlated to all features. Then we would like to remove A, that is F1, from the feature set. On the other hand, if this average 2 is highly correlated compared with this A, okay, then we would like to remove B, that is F3, from the feature set. If they are equal, then we randomly remove one. Why do we need to remove the largest one? The average is the largest. Why do we need to remove that? That is because for many algorithms we use for data analysis, there's one assumption, okay, at least one assumption. That is, all the features we use, that is here, all the features we use, for example, here, okay, all the features we use here should be independent. That is one assumption for many algorithms. I wouldn't say for all of them, but for many. So that is why many algorithms, when you apply, we prefer, column by column here, they should be independent to each other. Okay, that is for today. Apologize again, I use quite a lot of time for this lecture, but next week and the following week we won't have lectures. I think for some of you maybe it is time to catch up if you feel you are behind. So to catch up on your study, of course, please bear in mind you need to keep a good study life balance, and please keep safe and well. We'll see you in about 2 weeks. Okay, thank you.